This is Tom Dick. I'm a math professor and a math advisor for Texas Instruments, and this short video is part of the TI-Focus AP Calculus series. We're going to take a look at using the TI-84 to analyze a function where we're presented tabular data regarding the values of the function. Let's get started. First, we'll go to the stat editor, and that'll put us into a spreadsheet-like environment which displays our lists. Now these are the built-in lists called L1, L2, and so on. We're going to go up to that L1 header, hit Insert, and that's going to allow us to name our own list. Now the tabular data that we're presented has some time data and some corresponding values of the derivative of y, where y is the vertical position of a particle moving. So we'll name that first list time. And let's go ahead and enter the time data that was given to us in the table. Those values were 0, 2, 6, 8, 10, and finally 12. And you can see those values are not equally spaced. Now we'll go back up into the header, up to L1, and hit Insert again. And now we'll enter the corresponding values of y prime, the derivative of y. Imaginatively, we will name this y-der for y derivative. So I'm entering that name, and when I've completed typing it out, we'll hit enter, and we now have a new list called y-der. And now let's enter the corresponding y values or y prime values for those times. And at time 0, y derivative is 4. At 2 is equal to 8. At 6, negative 2. At time 8, we have 3. Time 10, negative 1. And at time 12, the y derivative is equal to minus 5. Okay, that completes our entry of the table of data that's presented to us. Now let's actually plot these as points. So we'll use the stat plot, and we're going to use plot 1, turn it on for graphing, and we're just going to plot the points. So I'm just choosing this first type, which is a scatter plot of points. For our X list, we can see down there we've got time. Let's enter that. And our Y list, we'll enter y-der. So we'll go back to the names of our lists and see y-der there at the bottom. Enter that. Let's see, how do we want the points marked? We've got some choices. I'll just leave it as a simple dot. And here's our plot. So this is plotting those ordered pairs of times and y derivative values. If we turn on the trace, we can actually trace through the values, which is nice. And now we're set up to answer some questions based on this tabular data. One of the questions we're asked is, what is an approximation for the acceleration at time equal 4? And to do that, we'll do a average rate of change between time equal 2 and time equals 6. I want to actually illustrate that. So you can see I've gone to the draw menu and pulled up line. I'm going to enter in the two ordered pairs, 2, 8 and 6, negative 2 over the interval that we'll use to approximate the acceleration at time equal 4. Now this line segment that you've seen drawn here, what we're after is the slope. So let's go back to the calculator, and I can see my ordered pairs right up there. So they're in the order x1, y1, x2, y2. So I'm going to do y2 minus y1, that'll be negative 2 minus 8, divided by x2 minus x1, which would be 6 minus 2. I'll do that little calculation, and it's very simple, of course. We've got negative 2.5 or negative 5 halves. Now another question was to do the average acceleration over the entire time interval that we were given. So this would be from connecting the points 0, 4 and 12, negative 5. And so if we draw that line, okay, that's connecting the very first data point, the very last data point, and the average acceleration would be the slope of that line segment. So we'll go back to the calculator, enter in -5 minus 4, that's the difference in our y derivative values, over 12 minus 0, which I guess would just be 12, so we'll just enter it that way. And so -0.75 or -3/4 is the average acceleration over the entire time interval. I'm going to go ahead and clear those out. And if we go back to our graph, we can see we've got our original scatter plot. We are also asked to approximate the definite integral over 0 to 12 of y prime using a midpoint Riemann sum with 3 equal subintervals. Now, I'd like to illustrate the rectangles that correspond to that midpoint Riemann sum. So I'm going back to the draw menu and calling up line. I'm going to draw a series of horizontal line segments. The first segment is going to go from time equals 0 to time equals 4, and I'll use 8 as the y value because that's the value of y prime at the midpoint 2. Now for my second line segment from 4 to 8, I want a y value of -2. So I'll do the line command again. We'll be going from 4, -2 to 8, -2. Again, that's going to give us a horizontal line segment, and it corresponds to the relevant side of our midpoint rectangle. And there we can see that. And for the final subinterval, we're going to go from 8 to 12 with a height of -1. So I'll pull up my line command, go from 8, -1 to 12, -1. And that should draw in for us our last horizontal line segment. And the main thing I'm trying to illustrate here is you can use this line command to give you some visual idea. Here we can see that what we want to do for the midpoint Riemann sum is add up the signed areas corresponding to those 3 rectangles. So let's go ahead and do that. Simple calculation. The first rectangle had a height of 8, width of 4. The second rectangle is actually a height of -2 times, again, that same subinterval length of 4, and our last rectangle, height of -1 times that subinterval length of 4. We add these 3 products together and we get our final result of 20. Now for the last illustration here, I'm going to go back to Statplot, and I'm going to change the type of plot from just points to connected line segments. So now let's go back to our graph, and notice we've connected, it's like connect the dots. We have straight line segments connecting our data points. In this problem, we were told that y was a twice differentiable function. So I just want to point out there's no way that this could actually be the graph of y prime because of those sharp corners. My main point here is it does give us a continuous graph, and we know that y prime would be continuous because it has a derivative. Keeping that in mind, since y prime is continuous and changes sign 3 times, we can see that it must be equal to 0 at least 3 times. Well, that winds up this video. For more resources like these, please see education.ti.com.